Okay, hello everyone. This is a quick lesson on binding energy. So I'm assuming that you first of all have watched the other video, and so really what we're talking about is the energy is equal to mc squared, Einstein's famous equation, where E represents the energy, M represents the mass. Now, in this case, it is really about the mass defect, the change in mass, and c is simply the speed of light. Okay, that mass defect is if you take the sum of all the parts within an atom, they don't always add up to the total. That difference in mass is actually the energy that is holding everything together within the nucleus, because if you think about, even if we just had a helium nucleus, you'd have 2 protons, 2 neutrons all together. There is a strong repulsion here, except for some sort of energy holding everything together, and that can be calculated basically through the difference in the mass using this equation. So let's take a look at what this looks like here. Now, the mass of a proton to 5 significant digits, and the proton mass of a neutron to 5 significant digits are given here. 1.6726 times 10 to the negative 27 kilograms for the proton, and 1.6749 times 10 to the negative 27 kilograms for the neutron. So this chlorine nucleus, 3717Cl, this will have 17 protons. So 17 times the mass of the protons, 1.6726 times 10 to the negative 27 kilograms. And that gets you a total of 2.84342 times 10 to the negative 26 kilograms. So that's the mass of all the protons. The mass of the neutrons, well, this will have 20 neutrons. 27. So the total mass of the neutrons, if you were adding up the parts, 3.3498 times 10 to the negative 27 kilograms. So the sum of the total should wind up being 6.19322 times 10 to the negative 26 kilograms, but the actual mass is only 6.13835. So we're going to subtract that. And it's that difference between the sum of the total, sum of the parts, minus the total, gets you that mass defect. In this case, 5.487 times 10 to the negative 28 kilograms. And that is your mass defect. So if we want to find out the nuclear binding energy of the nucleus, well, that's E equals mc squared. That's the mass defect times c squared. And this will get you an answer in joules, being the standard units here we're using of kilograms and meters per second. And when you calculate that, you should wind up with 4.9383 times 10 to the negative 11 joules. Now, if we wanted to figure out this per nucleon, well, we've got 37 nucleons. That's protons and neutrons together. So really, this question of just per nucleon, we're just taking this and dividing it by the 37 nucleons that we have, for a total of 1.3346756 times 10 to the negative 12 joules. Now, in each of these cases, I am keeping the calculator answer. I'm just writing out full digits. We've got speed of light, 3 times 10 to the 8 is actually on the formula sheet 3.00, and so our final answer in all three of these cases should actually just be to 3 significant digits. But as we were going through, we wanted to keep our calculator answer all the way through. So another way that we can calculate things with binding energy is based on the atomic mass unit. Now this is on your formula sheet, 1.66 times 10 to the negative 27 kilograms. Now a proton in this case would therefore have a mass of actually 1.007 atomic mass units, and this would have a mass of 2.6. Now this comes actually from that carbon 12 will have exactly 12 atomic mass units. And so the atomic mass unit accounts for a little bit of that defect. So protons and neutrons are actually just a tiny bit heavier than the regular atomic mass unit. So if we wanted to figure out the atomic mass defect within oxygen 16, well, they have 8 times 1.007 and 8 times 1.008 in terms of your atomic mass units. We'll get you 8.056 atomic mass units and 8.064 atomic mass units for a total of 16.12 atomic mass units. Now, subtracting that 15.994915 atomic mass units, which is the actual mass, gets you an atomic mass difference of 0.125085 atomic mass units. Now, if we wish to convert this into kilograms, we're going to take that 0.125085 atomic mass units, multiply it by 1.66 times 10 to the negative 27 kilograms per atomic mass unit. This is just that multiplying by 1 factor there, and you wind up with 2.0764 times 10 to the negative 28 kilograms as being the atomic, the mass defect. To find that binding energy in joules, we're going to just use, again, E equals mc squared. We've got the mass defect of 0.2764 times 10 to the negative 28. And this is 3 times 10 to the 8 squared. That results in 1.869 times 10 to the negative 11 joules. Now again, because most of these numbers, the last significant digit is actually 3 digits, we really should be rounding all of these answers to 3 digits. Right? Well, actually we got that one to 4 more. But 3 digits and 3-digit answers. Lastly, with this question, we're asked to convert this to electron volts. And again, keeping this answer, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, which gets you 1.17 times 10 to the 8 electron volts, or we could write that as 117 mega electron volts. Now, if you take a look at this equation, E equals mc squared. If energy is in electron volts and C is just c squared, we will actually sometimes see mass units of small things actually expressed in this electron volts over c squared. Just a little something. We don't deal with that a lot in physics, although it does appear on the formula sheet at some time, and that's really where it's coming from, is this whole idea here. So if we wanted to find the mass equivalent of 200 mega electron volts, that's going to use that manipulation that we've just got, E over c squared. 200 mega electron volts, or 200 times 10 to the 6 electron volts. First thing we're going to do is we're going to convert that into joules. That's negative 19 joules per electron volt. So the number of joules here actually is 3.2 times 10 to the negative 11 joules. And then putting that into E equals mc squared, or the manipulation, that 3.2 times 10 to the negative 11 joules over 3.00 times 10 to the 8 all squared. To keep things in proper units is 3.56 times 10 to the negative 28 kilograms. Taking a look at our last example here, we've got radium that is decaying into radon and an alpha particle. It's going through alpha decay. So in this case here, we're asked to just write the decay sequence. So radium, being 88 on the periodic table, is becoming radon, which is 86, and the alpha particle. Now we've been given the mass of each of these alpha particles, of each of these particles in atomic mass units. Okay, this is the 226.025410 atomic mass units. This one is 222.017578 atomic mass units, and the alpha particle is 4.002603 atomic mass units. So if we take a look at all that we have here, we've got 225.078383 atomic mass units in the products, but where we had 2.26.025410 atomic mass units as a product. So the mass defect here, the difference between those two, is 0.947027 atomic mass units. And if we want to find out the energy released in joules and electron volts, we need to take that mass defect and plug that in through Einstein's equation again. So E is equal to mc squared, but we're going to put this in kilograms first, times 1.66 times 10 to the negative 27 kilograms. That's equal to 1.57 times 10 to the negative 27 kilograms as being your mass defect. So you're plugging that into here with the mass. This is again 3.00 times 10 to the 8 squared, and that'll get you the mass, the energy released as 1.41 times 10 to the negative 10 joules of energy is released in this alpha decay. Now we're asked to also turn this into electron volts. So we'll take this answer, and 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And so you wind up with an answer of 8.81 times 10 to the 8 electron volts, or 881 mega electron volts. Okay, hope that helps. Thanks for watching. If you have any questions, please let me know.